Ken, one of my acquaintances slash one of my brother-in-law's friends lived in Trondheim for several years teaching English, like one does as a young man. My son goes to Japan, and he told me about a Chinese concept, which I think sort of roughly translates as social currency or gongxi. What has been your experience with that?
Yeah, I find a place, but I am on the yeah. Although I do love the streaming option. But I do like you guys added Although I definitely know this now, it's like a common core. I think it's just common core.
Oh, sure. Yeah.
Multiple factors.
He would have a friend who would go to the post office and 1 week he could send a letter in a package, no problem. And then a few days later, they would cut it off because his status had changed. Then all of a sudden, it
You seem isolated.
I'm sitting here screwing around. Do you have
Start what?
do you have time to talk briefly?
Sure, yeah.
Where are you in the old getting tenure process? You're in like
Year 2.
year two.
Yeah, so last year I was a visitor. But
Yeah.
in December when I got the tenure track job, my year as a visitor counted, even though my tenure track contract didn't start until this year. So as far as Reed is concerned, the superposition of a first year and second year faculty member, I'm required to go to both first year and second year faculty orientation meetings.
That is really amazing.
So I submitted my second year review, my second and fourth year review. I submitted my second year review in October. There are a lot of visitors that are hired into tenure track already, but it seems to be rare enough that they don't have a lot of established procedures for it, because I was not told about my second year review packet being due until 3 days before it was due, because they forgot about me and they had to give me an extension. But yeah, so that's it.
Okay. I had this idea a few years back, and it was basically an attempt to buy goodwill with local professors on the part of the section, which was basically to get professors together for a fancy-ish dinner, and basically we would not show up. We would basically ask somebody to lead. We would ask them to gather enough professors that it made it worthwhile, and then you guys would go have dinner on us, as a way of fostering community. So of course that died like a serious death in the pandemic.
Yeah, I can imagine.
And then my original goal was that we would have people who were someone who was senior enough as the group leader. So the person I first approached was Teresa McCormick, because she was third or fourth year in. Tenure was looking okay for her, et cetera, et cetera. So,
Shivani's your person.
what's it?
Shivani's your person.
Oh, okay.
Shivani is also at Reed.
Yeah.
I mean, there may be other people in other colleges, but I can only speak to Reed. Because Shivani just went up for a fourth year review, which at Reed is known to be like the real review.
Right.
And so she'll be at a nice spot where, provided when she gets the feedback back, which will happen in like a month or two, provided the feedback is good, she'll be in very good standing for tenure. It's never happened in the history of Reed that somebody got a positive fourth year review and didn't get tenure. But that would be probably a nice point for her. And she was also she's in the same predicament that I am. She was a visitor for 2 years. So it's a bit more severe for her, and probably a bit harder for her to.
Take out containers at the buffet, so feel free to help yourself or to go through. Thanks.
I did it because I watched other people doing it already, and I was like, Misha will be happy if I bring it back.
It's like maybe we could order less food, but that's neither here nor there.
It's funny because at faculty lunch, people do the same thing.
Yeah. That's okay.
And it's in this room, and it's the same food. Yeah, so I think that would be she'd be at a nice spot for that.
Yeah, okay.
But also, because she was a visitor for 2 years, I don't think that she really, she doesn't know as many people in the other colleges, so it might be a nice opportunity for her to meet people as well.
Okay. Awesome.
I'd be happy to introduce you.
I might just ask you to do that for me. So.
She also says yes to everything, which is like, you have to be careful what you ask Shivani to do.
I mean, and it doesn't have to be, yeah. Anyway, so I, of course, immediately thought of you. But when I was kind of like, oh, Teresa's like out, so now it's somebody else.
Yeah. And Shivani's really good at it. I think she would probably get something from it too.
That's, yeah.
Not that I wouldn't, but that
Yeah,
it's sort of, Shivani could also help. I don't know entirely how the tenure process works or where exactly they solicit letters from, but I could imagine this being a particularly acute moment where it's beneficial for Shivani to meet a bunch of people.
Yeah. I'm forgetting the name of somebody. Where is Mir in said process?
Mir just got tenure. Mir is on sabbatical this year. The sabbatical that you get the year immediately after tenure.
Well, that's cool.
Yeah. We miss them. It was nice when they were in the department last year. We're supposed to be staffed at 8.5, really 9. And with Mir on sabbatical, I'm currently 4th in line in seniority, and one of those people is Dan, who is department chair this year against his best wishes, but other than that, doesn't fill a bunch of the roles. So I am now appreciating how much work Mir did for the department last year.
I wish we had better turnout for Ginger.
Is this bad turnout? I am impressed that there are these many people.
This is the normal group.
It's also the week right before Thanksgiving.
Yes, it is. There's never good timing.
Yeah. I don't know. My impression for your talk, which I signed up for and then completely forgot about, was that you had a lot of students.
I had a fair number of students.
Nice. I think it'll be rough for us to get students this time. I advertised it to my students. They were like, I would love to go, but they have so many exams right before Thanksgiving break.
Yeah. That one was a talk that was well oriented towards students.
Yeah. But Ginger also had lunch with me and Jack Barbera from Portland State. So it was not just.
Yeah, it was funny because I actually emailed Jack Barbera. I'm like, it wasn't.
Yeah.
I did not say. I noticed your name is not on the list.
Yeah, he doesn't get the emails from the section. So.
Does the Portland State not email?
I have no idea how they work.
Yeah.
I don't know how I get emails from the section because Jack was like, oh yeah, I don't get the emails because I'm not a member. And I'm like, I'm also not a member, I don't think, but I still get the emails. And then I also get the emails that are forwarded by our administrative coordinator.
That's how most of Portland State gets the emails.
Yeah. Derek maybe just like filters them elsewhere and never looks at them.
I don't blame him.
But yeah, so we had lunch with Edgar earlier.
Well, I'm
today,
glad to hear that.
And Jack was like, yeah, I cannot do a 7:30 seminar. So he's like, do you know Elizabeth?
No, I do not know.
You want me to introduce you to Elizabeth?
Sure.
If you have a second. You seem to have a very important task.
No, I don't. There's literally like 3 viewers.
You want to come around that way? It's much easiest.
No, I'm taking it out, but also, who said you could be? I used to do it.
I do think it's really fun.
Yeah.
And my handwriting is so good.
Right there.
Yeah, I read that.
No, right. Let me just stretch. Yeah. Something into that doctor and stuff. Something like I mean, it was that. It's yes, but it's just like I had seen like that structure. They love writing stories. I think that would usually stop. Yeah. Everyone's writing.
And a couple of them like, whatever, but one of them was like, what part of it? And resolve conflict. I think while one of my postdocs, we had a quote. We had a quote up on the whiteboard. We had a quote in our research lab. And one of them was one of our postdocs down in the chair. But in this quote, one was up on everyone. I hope you enjoyed dinner and dessert. Take a few minutes to take a break or help yourself to some coffee or dessert, and we'll get started in about 5 minutes with our talk.
Yeah, because sometimes they're not in the office,
So yeah, she's been on our radar. Jen initially put me in touch with her. Yeah, she's been in the works for a long time. Yeah. Arthur is responsible for all the rights. Yeah. It's been she was at the last meeting and she carries our virtual EC meetings. And she was calling me. So yeah, I waited.
哎，你怎么样子啊？
Just about any question in Chinese can be answered with especially the delivery drivers when they come. You just say,
哎，对对对对，来嘛。
and that's it. And then the food arrives.
Yep.
All right, everybody, let's go ahead and get started. It's my pleasure to introduce Dr. Ginger Schultz, Associate Professor of Chemistry at the University of Michigan. She's been on our schedule for about a year and a half now, and due to COVID, things have been delayed a little bit, but we're really happy to welcome her here this evening. So please join me in welcoming her. I promise we've done our best to scrub every C we can find from your name, various places, and it's been an effort, but we think we could accomplish it. So, anyways, please join me in welcoming Ginger.
Yeah, so thank you so much. I'm really delighted to be here and have this invitation. I am originally from Seattle, and I went to the Evergreen State College as an undergraduate, and then to the University of Oregon for graduate school. So it's really lovely to be back in the Pacific Northwest with all the green trees, and I really enjoyed chatting with all of you. So thank you so much for the invitation. So I am going to be talking about broadly capturing student reasoning and assessment of language structure and behavior. We'll get that's loose. So I will tell 3 stories, and I selected these 3 stories More because the audience here, I wanted to be able to convey to you kind of the scope of what you can do in education research and some of the things that we've done in my group. So that's what we'll be doing. So I want to start with thinking about, talking about reasoning. So we can start with a common definition of what do we mean by reasoning. And so this is from psychology. So thinking in which logical processes of inductive or deductive character are used to draw conclusions from facts and premises. So it's a little bit more than thinking, right? It's a little more precise. I've highlighted logical processes and facts or premises because when we're investigating student reasoning, those are the things that we're trying to capture. What are the processes they use to think through a problem or a task? And what facts or premises are they drawing on when they do that? So that's where we're starting. If we look at the chemistry example of this, we can kind of unpack this idea of reasoning a little bit with this particular task, which is ranking reactions from least to most favorite, and these are all acid-based. You can think of it that way. And there are ways that students might approach this. Hydrochloric acid that may or may not serve them in solving this problem. Or they might actually draw on things like periodic trends to really help them work out the things. So that's what we're interested in. Not necessarily, did they select 1, 2, or 3 or whatever in the ranking that we might expect and what their answer was, but how did they get to that answer? That's what we want to learn about. So you can even further break down reasoning, and we've been, as you might imagine, in chemistry education research and science education research, we've been thinking about reasoning in a lot of different ways. And so these are some of the different versions of reasoning that have been looked at in chemistry education. So you can think particularly about reasoning using representations, mathematical reasoning, say in kinetics or physical chemistry where math comes in to play, conceptual reasoning, mechanistic reasoning I'm going to be talking about tonight, chemical reasoning, and argumentation. So these are just some of the areas that there's a broad set of research that is focused on this. So we're going to start here. My first story, or the first project I'm going to talk about is capturing reasoning during NMR problem solving. This was published a year or so ago in the Journal of Organic Chemistry. And really we're interested in what kinds of reasoning do novice chemists use as they begin to learn to interpret NMR spectra in organic chemistry. So to think about what this might look like, it's really important for us to think about NMR as a problem, or an NMR interpretation task as a very complex sort of problem. So if you think about just looking at the spectrum, we think about each line, as we know, contains a lot of information that the students have to decode and sort of figure out, right? And just on a basic level, chemical shift, splitting, integration, and number of peaks, we know that it can get more complicated than that. And then they have to relate those back to some of the other things that they've learned, these foundational things that in terms of the structural features and implicit properties that they can interpret from the various representations that we use to describe molecules. So Lewis structure shown here, for example. So they have to be able to take all of that information in and process it in order to interpret this spectrum. So a novice, someone who's first learning to do this, may find each individual thing somewhat challenging. And so you can imagine, bringing all of this together is quite a lot for them. Whereas an expert can do a lot of this automatically. So they can look at a Lewis structure and automatically see, for example, that the oxygens or the carbonyl group will have a polar bond, for example, without even really having to think about that very much. So they can do that automatically, and they can also more quickly select what they should pay attention to and narrow in which they should focus in on the spectrum. Okay, so we were very interested in this. There has been some research before we started doing this in kind of thinking about this. What does it look like from a novice perspective to an expert perspective? So what we know from this prior research, or what we knew, was that novices sometimes have inaccurate ideas, or they draw on inaccurate facts or premises. They use more of a rule-based understanding and rely on those rules and heuristics very closely. They are typically only able to make decisions based on single variables in the problem, and then they evaluate multiple variables at the same time and weigh them together when they're deciding, making different decisions during their reasoning process. And then they can very easily triangulate with other data and complementary spectra. So we're interested in this. We know what a novice looked like. We knew what a novice looked like. We knew what an expert looked like. So we wanted to really map what happens along the way as you're developing this expertise. Okay, so that's what we were doing. So the way that we did it was to develop a set of tasks that we could engage our participants in and be able to investigate their reasoning. So our goals in developing these tasks were first to figure out what were some features of what might be what seems like a relatively simple interpretation task. What are the different features that might make this more or less difficult? So we interviewed faculty who teach organic chemistry and also who have organic research labs to kind of identify those things as we were designing the tasks for our study. And then we developed and piloted a set of them, and then narrowed down to identify the ones that would present the greatest range of difficulty for us, and help us to learn the most, I guess, from our participants. So we ultimately ended up with a set of 3 tasks that all sort of look like this. We wanted them to be at least somewhat closer to what a practicing organic chemist would use. So we essentially we would present them with a Lewis structure like the one shown here, and say, okay, you ran a synthesis where you were hoping to make this product, and you have 2 spectra here, an IR spectrum and a proton NMR spectrum, and you now need to look at that and decide, did I make the product or not, right? So the answer for them is a binary one, yes or no. We weren't that interested in whether or not they got the correct answer. Somewhat interested. We're more interested in the process of getting to that answer, and that's what we were trying to do with that. So all of the tasks had a similar format, and these are the 3 different synthesis products or molecules that with corresponding spectra that for the 3 tasks that they did. So this is how we gathered data. So we used a combination of eye tracking and something called a retrospective think aloud interview with both undergraduates who had just finished their Organic 2 class, and then also with graduate students from organic groups in our department. So we had 18 undergraduates and 11 doctoral students. So for eye tracking, if you haven't heard of this, essentially this is what the device looks like here. It fits on the bottom of your computer screen, and it measures the glint in your eye as you look around at things on the screen. So you can imagine having a spectrum on the screen, and whatever you look at, how long you look at that thing, and then how often you move between different features in that thing, that's what it's measuring. And the reason that's interesting to us is because what you look at, what you're attending to with your vision, is connected to what you're thinking, right? And so that can tell us something about the process. And then we coupled that with this retrospective think aloud interview, and I'll tell you a little bit more about that in a second. But we needed to hear from them, right? So that we didn't have to infer as much about what they were thinking, and that's what they would do. Okay, so that's what that looked like. So this is the prompt for the retrospective think aloud interview. So they would solve the problem. We would measure what they were looking at with the eye tracking device, and then we would, using the software, play back to them what they were paying attention to. So this is what they would see. And while they were watching this, we would ask them to think aloud, or to replay aloud what it was that they were thinking about. So they could pause and say, I was looking at this amide group over here because I was thinking about the splitting and wondering if it connected to this peak down here. So we can then connect what they were looking at to what they said that they were thinking about. So that's how we did that. We did a lot of analysis, and I won't talk about that process, but essentially the interview data, or the retrospective think aloud interview, we had transcripts, and we evaluated the transcripts for themes, and we found 5 themes of things that came up in their reasoning process. Foundational aspects, which are just the shift, number of peaks splitting, and that sort of thing. The N+1 rule deviations, variability of data, visual spatial aspects of symmetry, and that sort of thing, and then practical aspects, and that came more into their experimental and And for each of these 5 areas, we mapped that progression of understanding. And I will talk about just one because I want to get to other projects. So I'm going to focus on how the N+1 rule came into their reasoning along this progression that we're talking about. So in terms of their progression of understanding, beginning students, in terms of the N+1 rule, would make a lot of invalid assumptions, just applying the N+1 rule to everything and not recognizing that there are exceptions to that. I can see some nods because I know it sounds like there's folks who are taught and more in this room. And then moving up to where they're starting to have doubt. Okay, maybe there are instances where the N+1 rule doesn't apply, but not necessarily knowing when that is. And then having some assumptions about when it does not apply and some additional knowledge in terms of when that might be. But if we probed more deeply, they couldn't fully explain that. And then at the highest level, they knew when it didn't necessarily apply, and then they could say a lot about that, essentially. Okay, so here's kind of an example of what that might look like. So for this particular task, coming back to this AMID that we're talking about, a novice student, someone at the bottom of the progression or the beginning of the progression, they would think, okay, well those 2 singlets can't possibly be the AMID or the alcohol, for example, because those should be split, and they're not, they're singlets. So they would say that this wasn't synthesized because they didn't think that the spectrum matched. On the other end, they recognized automatically that, or were familiar with the fact that amides and alcohols are often not split in the spectrum. And they could say, to some extent, why they think that is, but they didn't necessarily have a really detailed understanding. So for example, if you were an organic chemist that had been working with amides for a long time, you just understand that there's this rotation that happens, this slow rotation around the amide bond that influences that. So one of the faculty that we talked to happens to do a lot of work with amides. So this was something that they were very familiar with, but not necessarily every one of our participants would have known this. Okay, so if we summarize all this for the 3 tasks, then and comparing the big U and little g as undergraduates and PhDs are the doctoral students, then we can kind of see along this progression from lower to upper level what we're seeing for 4 of those areas of understanding, just in terms of the absolute numbers. And you can see that the doctoral students, thank goodness, were on more of the upper level, and with some tasks, the undergraduates were more on the bottom, but not completely. There were some undergraduates who had more sophisticated understanding depending on the problem, and those may have been students who were doing organic research and had spent more time with NMR. But this was sort of a validation check for us in that, if you're proposing a progression, then you would want to see that novice students, or the novice chemists were on the lower compared to more experienced chemists. Okay, so now we'll move over to the eye tracking results. So broadly, the doctoral students had a more sophisticated understanding, and not only that, in terms of the eye tracking, we noticed they were much more selective in terms of what they were looking at and efficient in terms of processing that. So we can break that down a little bit in terms of undergraduates. They exhibited what is called uninformed bidirectional processing of all information, meaning that they were just randomly looking at things, and they would go back and forth between things on the task a lot more, whereas doctoral students were informed, so they knew what they needed to look at. They would go to that, and they often didn't have to return to that. So this is how we captured that for each task. So we had areas of interest, which I have shown here in different colors. So the directions at the top, the Lewis structure, and then different features of the IR spectra and the NMR spectra. So we would look at something called fixations. So how long are they looking at this particular area of interest? And then the transitions, how often are they, for example, going between that peak and other things on the task. And we did some simple statistics. We used something called a U statistic, which is kind of like a t-test, but for non-parametric data. And in order to compare the differences between undergraduates and doctoral students, and each of the areas of interest is shown here. So we have fingerprint region, the M and NMR peak, the axis, and the IR table, just to compare. And we saw that there was a statistical significance with a really good effect size, actually difference between the doctoral and graduate students, showing that indeed what they were looking at was quite different. We moved these into, or pushed this into a chord diagram. I'm going to walk you through these a little bit. So essentially around the outside of the circle are those areas of interest that I was talking about, and they are color-coded, just like I showed you in the breakdown of the task. So in green on the left-hand side, or I guess on both sides, green is basically all of the areas of interest on the NMR spectrum. In blue, we have the IR spectrum, and then we have the molecule, and then they were provided with two tables. And you'll notice one is for undergraduates and one is for doctoral students, so we're comparing between the two. And then each of the chords, which are the bands that are moving between the circle, those are the color of where the transition originated. So if it's green, it started with the NMR, some feature on the NMR spectrum, and then ending up where it went to. And the width of the chord has to do with the number of overall times that they made that transition. And you'll see, and then we just showed the chords for whether or not it's statistically more often, right? So you can see that undergraduates have a lot more chords, so they're going back and forth a lot more number of times between different features, whereas the doctoral students only have one chord shown, because there was only one thing looking between the ppm axis and the molecule. That was what they spent a lot of their time doing. So this is just one way of representing what we saw in the eye tracking data. And again, it comes back to these things that I said earlier: uninformed searching and bidirectional processing for the undergraduates, and then informed searching and unidirectional processing for the graduate students. And you can see that this was the same for all three tasks. We saw the same phenomena, so it's consistent across the tasks. And so that kind of wraps it up for this story. So essentially, we saw that the primary difference between the undergraduate students and the graduate students was that the graduate students were more easily able to pick up this implicit information and think about its effect on the spectra. And so our implications here are that if you're teaching NMR, really focusing on these 5 areas of understanding and helping them move up those progressions. And then in terms of the eye tracking data and the visual information, novices do not readily identify relevant information. They're just looking at everything, and they spend a lot of time just searching around the task. So in terms of instruction, really helping them to systematically mine the data and practicing, giving them opportunities to practice with pattern recognition is what we recommend. So that's where we landed with that. So that's the first project. And that's the project that I would say is the most obvious chemistry, right? So as we're moving along, we're going to move a little further away from where the chemistry is as obvious. So our second project is thinking about reasoning, but capturing that in writing that students do. And this is going to be coming out in December in a book published by the RSC on reasoning and organic chemistry. We're going to think a little bit about a different kind of reasoning, mechanistic reasoning. So mechanistic reasoning doesn't just apply to organic chemistry. I know we like to talk about mechanisms in organic chemistry, but mechanisms appear all across science, right? So photosynthesis, for example, is a mechanism. So you can think about it that way, but of course we're using this in organic chemistry. So if we think about how students learn mechanisms in organic chemistry, they learn through seeing drawings that we do and reproducing the drawings, and they're able to often draw those arrows in the electron pushing formalism in the way that we want them to. But often if you ask them to say, what does this arrow mean? They can't really explain that, right? So that's where the reasoning comes in and why we're interested in that. And connecting back to the writing to learn, this is something that I'm really interested in. We all help students learn to write in chemistry. They write lab reports and do different things like that. The idea of writing to learn is that the actual process of writing is connected to thinking, and so it helps students to learn, right? And it can also help us to learn what they think. And it supports a variety of learning objectives. It's really versatile. Of course, we know that it supports reasoning, along with the other things that I've shown here. It also promotes metacognition, which is thinking about thinking, and them becoming aware of their problem-solving process and their own reasoning. And then it also elicits students thinking. So it's a really good formative assessment for helping us to really understand where they are in terms of what they understand. Now, writing sounds great, but if you're like me, when I teach organic chemistry lab, and I have 800 students. 800 students with writing? That seems crazy, right? So we're really interested not only in helping faculty to use writing to learn, but also in helping them to be able to do that in a way that's feasible for them, right? And gets around a lot of the constraints that you might, I think all of you imagine, comes along with writing. One of the solutions to that is to use something called automated text analysis, and as a way of giving formative feedback. Because I can't read 800 pieces of writing, I would spend all year doing that, right? But if I can use automated text analysis, maybe that'll tell me something about the student's writing, and that's what we're interested in. Some folks have been working on this for a while. There is someone at the University of South Florida who does this, and then also at Michigan State with shorter pieces of writing. We use a lot of longer pieces of writing, so we wanted to see if we could capture that. And that creates some different problems for teaching a computer what you want to look at. But we were interested in that. And the other thing that you might imagine is, for each individual writing task, maybe you could create a model, a computer model to read what you want to, or to predict what you want to from that writing. But then you have to create a whole new model for every assignment, right? We didn't want to have to do that. So one of our goals was to develop models that we could apply to multiple pieces of writing, maybe multiple organic chemistry reactions. So that was kind of the goal of this project, was to help faculty develop automated text analysis models that can provide formative feedback for students to help faculty to be able to use that in their classroom. So this is an example of a writing assignment that actually I use in my course. And essentially what we wanted students to do was to be able to compare different reactions and to write about that, right, in their comparison. So on the left-hand side, you'll see there's 3 schemes, and we wanted them to compare the 3. The first one is a traditional Wittig reaction. The second one is a base-free Wittig that was more recently reported. And then at the bottom, scheme 3 is the same conditions for the base-free Wittig with a different substrate for which it doesn't work, right? So accurately, as you see on the left. So essentially, and I can't show the whole writing assignment here because you would be reading, and I don't want you to have to spend all your time reading the slide. But essentially, we provide a rhetorical, the rhetorical elements. So we specify a role for them in their writing, tell them who their audience is. We provide a context and a task, and then a genre. And then these are 350 to 750 words. So maybe 2 or 3 pages of writing about this. They do peer review, and they also revise their writing based on that peer review. And then these were the specific instructions that they're given. So we want them to explain key structural and electronic features and the role of those in the mechanistic steps of the base-free reaction, which I've shown in scheme 2. We wanted them to compare the reactions, the traditional and the base-free, and explain why one does not require an external base, based on using what they had talked about in terms of the mechanism that they were proposing for the base-free, and then also explain why it doesn't work in all cases. Okay, so that's one task. We had multiple assignments that we did this for, and actually 4 different reaction types, because again, we wanted to create a model that would work for more than one assignment and one reaction. Okay, so we gathered all this writing, and as I said, I had 800 students for multiple assignments. I've been doing this for several years in my class, so I have thousands of pieces of student writing that we can do this with. And this was essentially the framework that we used. It's a framework for mechanistic reasoning. It was actually developed to be used across science, but it was adapted by some folks to be used specifically for organic chemistry. I don't necessarily want you to read all of this, but for example, one of the things that we would be looking for in the writing is properties in the molecules that they were talking about. So for example, if they talked about, for the ylid, they talked about the acidic proton on the carbon that is tied to the phosphorus cation, it's easily deprotonated. So they're recognizing that there is something about the nature of that proton that is important in the mechanistic step that wouldn't necessarily be obvious to them if they were just looking at the Lewis structure. They had to think more deeply about it. Okay, so we used this as a framework to analyze many pieces of writing by hand, so we read through them. And this is what that might look like on an individual sentence level. So this is color-coded, and these themes come from the framework I showed you on the previous slide. So for a single sentence, you might see all of the codes, as we would call them. So in terms of a property code, for example, we noticed that they talk about the oxygen having a positive charge, so that is a property that they attributed to the oxygen, so we would give that a property code. There were different activity codes, bond making, non-electronic and electron, so they talk about something bonding with something else or a bond breaking. And then the non-electronic, we've all seen this, the water molecule will attack. So students like to use that word, attack. Or if they're specifically talking about electrons moving around, that would have the activity code for electron. And then we had also a cause and effect code. So we have these properties, and this particular thing happens, and that results in this other thing. And thus got the cause and effect code. So the single sentence could have all of these codes together. So we did this for many, many writing assignments in many, many sentences. And this is what we found. Without even doing anything with the computer yet, essentially for 3 different reaction types, for all of those different code types that I was talking about, this is the percentage of students per assignment that had that. So you can see what this really told us and what we're interested in is the assignment eliciting the reasoning? So does the assignment do what we think it's going to do? And we think it does. Because a large number of students, or the vast majority of students were getting most of these codes. The ones that had the lower percentages actually made sense. So racemization is, for example, we have a stereochemistry code, but that's not necessarily important for hydrolysis and Wittig reactions, so we wouldn't expect to see that as much, and so forth. So it looked like our hand coding, so to speak, actually worked, and again, that the assignment was eliciting what we hoped it would. So then we began feeding it into the computer to try to teach the computer what we were interested in seeing in the writing and what we wanted to learn about. So we did this at the sentence level, just like I showed you, but we taught the computer what we were looking at the sentence level. We ended up doing this just with the model for 80 assignments, and sentence by sentence. And we divided this up for a training set. So if you're familiar with machine learning at all, you train the computer based on a portion of your data. You then use a portion of your data to test to see if the computer is getting what you think it is, and then you save some aside for validation of what you're doing. We tried a number of different machine learning models, but we ended up using something called a convolutional neural network. I only understand that somewhat, so don't ask me any questions about that later. And then we evaluated the accuracy, first just basically compared to the hand-analyzed set, and then with a number of common metrics, Cohen's kappa, Matthew's correlation coefficient, and then true, false, positives, and negatives, if you happen to know about that. Okay, so this is the result of our convolutional neural network model and what we were able to find out. So we had really good accuracy along the left-hand side. You can see, coming across for each of those codes, we have accuracy, and then we have Cohen's kappa and the Matthew's correlation coefficient. So just to orient you, what would you want to have happen, right? So for us, a cutoff that we would be interested in is 0.7 for any of these values. And actually, if you get 0.7, that's better than what the Educational Testing Service does for pieces of writing like this. So for most of these, we're getting not only 0.7, but far above that. And if you think about what I mentioned we want to use this for, we're not using this for grading. We're using this for formative assessment. we want to be able to come back and say, is this student, for example, using causal reasoning? And can the computer tell us that? So then we can go and do something in class to help the students start to use causal reasoning more. So we were really happy with that. One place where we didn't quite get where we wanted to on the model was with cause and effect, where there was no mention of electrons. That was actually harder. We were below the 0.7 value on that. And if we come back to this sentence, thinking about the cause and effect here, not only are there fewer words overall, but these are more colloquial terms, and so it's harder for the computer to pick up. So we weren't surprised by that. But we were happy enough with these values that we're now building an interface, actually, and that's kind of the next step. So just to summarize from that part, we did a hand analysis of the assignments, showing that the assignments worked to elicit the reasoning that we were interested in. We were able to develop a machine learning model that was able to have a really good accuracy on almost everything except for the causal reasoning. So we're actually working with our ACS to develop an interface, and we just submitted a paper on this, so the interface will be coming out soon, and hopefully I'll be able to use it in my class. So we'll see. Okay, so that's the second story. So now I'm going to finish up talking about something that really isn't that much about reasoning, but it's enough, and I really wanted to talk about it here. So we have a completely different project working up in Arctic, Alaska, in collaboration with the science faculty up there at a tribal college. Some of my students actually came in the last year and talked about that here at Reed College, so I'm not going to get as much into the details, but I just wanted to include it here to show you, again, the scope of what we do. So this is just a picture of some of us and students out on the tundra collecting snow samples that were part of this project. So before I begin, so this is a culturally relevant education project. It's a collaborative project at a tribal college. I am not Native Alaskan, so I don't have any business doing this on my own. And I was very fortunate to have collaborators that brought that expertise and that experience to the table, as well as folks that are actually teaching at the college. So on the left-hand side, you'll see Linda Nicholas Figueroa. She is the only science faculty at this college up in the Arctic. And then Daniel Wall is a social scientist, and he teaches social sciences up there. Carrie Pratt is my colleague at the University of Michigan. She does environmental analytical chemistry. She's been working up there doing that kind of research for a long time. Corey Sidwa Erickson, he is Inupiaq, which is the Native Alaskan community that we're working with, so he helped to make sure that we were doing things appropriately and to provide a lot of guidance with that. And actually, he and Carrie really conceived of this project together, so it was kind of his vision, along with Carrie, for doing this. And then Jeff Spencer and Daniel Maxwell here at the bottom. Again, I just wanted to really put this out there that for this kind of project, it's absolutely important to collaborate, to do it in a collaborative way. And then we had additional contributors. So we had Inupiaq elders and other community members who would come into the classroom and interact with students. When we would go out onto the tundra, we had logistical support and bear guards, because there are polar bears. We have polar bear training. The bear guards are incredibly knowledgeable, actually, and we learned a lot from them all the time. Students, and then the NSF Advisory Board for that. So, so we had this collaborative project. So why are we doing this? I like to start this with thinking about, that this idea that I think has been put out there more recently, which is that science is better when we invite more folks to the table, right? So I like Jane Goodall as an example of this, and many of you may know that when she started doing research, she didn't have a college degree. She was a young woman at a time where there weren't a lot of, or hardly any women in science, and she traveled to Tanzania and studied chimpanzees there and just figured out how to do it. She did it in a completely different way than what was the convention, right? And she transformed things in a way that has had ripple effects over the years ever since then. And she did that because she brought a different perspective, and she brought herself to the work. So it does matter who's involved in the scientific enterprise. And so not only expand that view as scientists, but also bring that into the classroom. And that's what this project is really about. So our goal with that in mind was to develop what we're calling a unit. It's not quite big enough to call a curriculum for students at this college, and it should be culturally relevant, engaging students in inquiry about snow chemistry processes, where they live in the Arctic. And then when we were done with the project, we really wanted it to work sustainably so that the instructor would be able to continue using it after we were done, and in a way that made sense for the students and her particular context, and then stay on our community. So this is a framework for culturally relevant education. It has 4 tenets. The first one is developing connections between cultural references and academic skills and concepts. I think that's the one that's most obvious from the name, culturally relevant chemistry, that's what we're trying to do. And then the others are engaging students in critical reflection about their lives and the world around them. So that comes in a little bit into this reasoning. Facilitating their cultural competence, and then also helping them to identify and dismantle oppressive systems through critique of discourses of power. That is a mouthful. It's also a lot to think about when you're designing and to do. But all 4 of these elements are really important to culturally relevant education. Mostly what we're going to see, or what I'm going to talk about, is number 1, which is the developing connections between cultural references and academic skills and concepts. Okay, so a little more about the context of where we were doing this. So this is in the Arctic. It's in the northernmost point of the United States, where that star is shown, and then the circle is just part of the Arctic Circle. So it's way up there. And it has been the home to the Inupiat people for more than 10,000 years, and they would say time immemorial. And that means that they have a lot of knowledge that has to do with thriving and living there over that time. So they're very knowledgeable, and they have their own science around all of that is associated with some of the things I've shown here and many other things in terms of subsistence hunting, how they navigate the sea ice, which is really fascinating. I can tell you about some books that you might read if you're interested in that. Food storage technology is actually really interesting as well. And then they bring into that their family and community values, which we saw a lot of when we were doing this. So at the college, at Illicellewaet College, we weren't the first people to we didn't bring culturally relevant education as a thing to them. They're already doing it. They bring the Inupiat knowledge into every single class that they have there, even welding, right? They have something like that. That's their mission. So we didn't bring that to them. We were really learning from them about how to do that. I think the thing that we brought was the chemistry, because Linda is more of a biologist by training. So we were able to bring that, and we learned a lot from her and a lot from what they do up there throughout this process. Okay, so thinking about how we designed this unit, really we wanted to design it around bringing all of these resources together. So these are sort of the cultural connections that we wanted students to be making. And we divided these, and this is our artificial division. Students didn't necessarily, and community members don't necessarily think of it this way. We have local resources that they have in their community. For example, non-Inupiat community members who've been living up there for a long time, they have a Bureau of Land Management and other folks that are knowledgeable. Traditional resources in the center, there are tribal elders that I mentioned. They came to the classroom, bear guards, the whalers and subsistence hunters obviously know a lot, and then scientific resources. So in Agavik, this is actually a hub for Arctic science, and there's an entire science complex up there. So there are a lot of resources for students there too. We wanted them to be able to bring all of these to bear in the unit that we designed. So we represented this as kind of a braid going around, where you can imagine weaving all of these together and trying to tightly connect them, and thinking about it that way. And the unit had 3 parts. So I'm going to walk through each of the parts and use those to kind of illustrate how the students engaged with it. So the first part was information gathering. So part of this, as I said, we had Inupiat elders come to the classroom and tell stories about snow and ice and things that were related to that, and the knowledge that they brought forward to their community. They could also gather resources. but also scientific resources as well. They also designed interviews and went out and interviewed community members. Some were elders, some were not. Some were people who were hunters or whaling captains. They did a guided inquiry. It's sort of a POGL, if you know that, but we can't call it POGL because it's copyrighted on snow chemistry literature. And then they summarized all this together. They tried to synthesize it and develop a research question. So this is just part one. So this is an example for one student of what that looked like. So for this student, when the elder came to the classroom, they learned that tutu, and this is the Inupiaq word for caribou, they migrate to the ocean in search of salt and salt along the way. And so that kind of sparked something in the student. They were interested in that because they themselves had been hunting caribou from a young age. And so they pursued that, and one of the things that they did was read an article on chloride concentration by snow dove as a way of connecting those together. And all of those and other things they pulled together and designed this research question, or came up with this research question: what are the differences in chloride concentration based on proximity to tutu herds and snow depth? So then that brought them to the next part. Oh no, I'm going to get ahead of myself. So here's some examples of some other research questions that students came up with, which illustrate that same thing. Essentially, how were they connecting the traditional knowledge and the local knowledge together with the scientific knowledge to formulate their questions. So does chloride have any effects on the types of snow used to make igloos in Nunavut? Does sulfate and nitrate found in snow contribute to poor air quality? So there were some students who actually weren't from Nunavut. They were other places in Alaska. Can chloride concentration in the Scanlon River contribute to the disappearance of tomcod fish? So we adapted for the students. They could measure ions in water rather than from snow. And then what effects would changes in chloride levels have on snow used to insulate traditional ice cellars? So this is the technology that I was talking about. This is a picture of an ice cellar going down, and this is someone moving whale meat, bowhead whale meat down in the ice cellar. So they connected their question back to this really important technology for you, because, or for them. If you can imagine how big a whale is, where do you store that and have enough of that? Okay, so that was the first part of the unit. The second part is collecting and analyzing data. So they designed an experiment based on their research question. How do I answer this research question? They had a session with an Arctic researcher to help them think through what they were doing. They then went out and collected snow, which is the picture at the top. So that's them collecting snow. They did measurements, and I'll show you what that looks like, and then they did a data analysis from those measurements. So this is a picture of students and one of our graduate students working on the project about collecting snow. So they would dig a pit and measure the depth, and they had a whole process for collecting snow in a way that didn't contaminate it, and record keeping. And it is very cold, just as cold as you might imagine. I did this with them last spring, and it was very cold. And then they would bring the snow samples back to the lab, and there were two ways that they were analyzing it. So we started, when we initially started, they would do a titration, but this is less than ideal because it has chromium in it, and they didn't want to have to deal with that waste way up there because it's very expensive to handle. So then we moved to an ion selective electrode that they could do, which was much easier. So this is an example of a student taking a measurement with the ion selective electrode, and then the plot here of chloride concentration that they were getting. Okay, so then moving to the third part, really what we wanted students to do is not just to do the projects, but we wanted these to come full circle and inform the community again, right? So the community informed what they were doing, and we wanted them to be able to bring their results and talk back to the community. So the last thing they did was present their results through stories and reflections. So not just a PowerPoint like I'm giving right now, but through a mode of communicating that would match more with how the community communicates together. So that was the last thing. So this is an example of, so the student did use a PowerPoint. This is an example of some of the data that they analyzed. And then on the right-hand side, you'll see a picture here. So of where these were collected right there on that northernmost point. You can see the dots right there. Some are further out on the tundra and some are right along the ice in the Arctic Ocean up there. Okay, so that's what it looks like in the full circle. From a research perspective, we were interested in how the students were bringing that together, and that's one of the things that we're working on. We're also really investigating our collaborative design process. So as you can imagine, we had 6 people who all had very different perspectives and different values and things that they wanted to see in that, and so we captured a lot of data on that we are writing up right now. And I did include it here because I wanted to talk about more of the projects that we did. But essentially, this is kind of where we left things. We have a sustainable, usable unit that has completely been transferred over to our collaborator, who's the faculty up there, and they are continuing to use it and just modifying it, using it in different classes and in different ways up there. I would say, and we often get this question, that's great, you're in this, this is happening in an environment where there's a very clear cultural, set of things to draw from, but many of the general components, I think, are transferable, and there's a lot of literature. Actually, there were a number of good articles in the recent DEI-focused issue of the Journal of Chemical Education, and at least 2 or 3 of them that were also on culturally relevant things in the lower 48, so it doesn't have to be, there are other ways to do this in your context if you're teaching. And what we're doing next now is going through the same process with middle and high school teachers in this same community up there, helping them to go through the process of designing culturally relevant science activities with their classrooms. Okay, so I will finish up with acknowledgments. So this is my research group. Over here, we were at the BCCE conference just this past summer. And then on the right-hand side, I just listed the folks that contributed to each of the projects here, and those sources for funding. And with that, I think I am ready for questions.
So, on your second project, that's really interesting because I think one of the things that we run into all the time is we come up with an assignment, we run it for a couple of years, and while we don't really know if it's working or not, we don't have quantifiable data. So the hand approach that you do, well, we could do that. I mean, it's not beyond our capabilities, but the computer approach is really interesting. So is it possible to look in those articles and extract that method, or are you more hoping to make like a institute or a resource that people at small colleges like us could like send a bunch of data to and get like a score back?
That would be, a really good next step for the project, because I said we're just building an interface, and then I will be the guinea pig for the interface in my class, and then if that seems to work well, then we would like to make it available to other folks. One of the things too, we can't share, the student data, but we can share the code.
Right.
So if someone is able, they could use the code and try that out on a different writing assignment that they think elicits mechanistic reasoning. And we actually have other projects too that are sort of in the same stage that support writing that would do the same thing.
Okay.
So
because I like your example. It's an example of an assignment that is getting good scores, but well, maybe we have an assignment that's getting like 0.4s and 0.5s, so that would be really interesting to be able to apply a standardized approach and actually start getting quantitative data on the success of our methods. So that, thank you. I'm really interested.
It's been, I've been using writing in that class for like 6 or 7 years, and we've been making tweaks to the writing assignments, and so one of the things we're using this for is to see, did that shift, as we made these changes, to think, did it happen? So it can be a one-time thing, but you could also, if we create an assignment and then we make a change to it thinking that will improve it based on what we see, but we don't really always know. So also, as you iteratively improve something, it can help with that as well. And, we'll see, but I have a team of people that are figuring this out. Like, so if I was doing this on my own as an individual instructor, I don't know how to do it.
first project, the novice to expert reasoning that you were looking at, what was the thought process? Sorry, excuse me, I haven't been talking for a while apparently. What was the thought process around selecting doctoral students instead of postdocs or faculty for the expert community?
Yeah, we could have recruited Dr. Schultz. I mean, I would love to get some of my colleagues on the eye tracker and see how that goes. But we had mostly interviewed them. We were really interviewing them to design the tasks. But yeah, it would be interesting because not all graduate students got that upper limit, and they're really, for the AMIT rotation example that I showed, we really didn't see people who were knowledgeable about that. So that would maybe be a ceiling for that, but we were pretty close to, where people were really knowledgeable and they were really solving well. So we didn't feel like we needed to add postdocs, but we certainly could have. I think Megan, who's a student who worked on this, was, it's very, very data intensive, and so she wanted to go with, at some point when she was seeing what she needed to see, she kind of stopped there so she could graduate. So.
Thank you for not having the little eye chart thing helping us.
Oh.
That's a pretty amazing thing, and students are volunteering for this?
Yeah.
Yeah, so that's not an invasion of their privacy or anything like that.
No, they volunteer, and we have a whole consent process and
Sure.
everything
And
that
so
we
they
do.
can put it on their computer and watch what they, you don't have a chat option up there, right?
No. I think we go over here first, yeah. Sorry.
Have you been able to use the information that you get feedback from Project 1 to design activities or teaching assignments so that you can build it up faster than just taking the beginners?
Yeah, so I use that to develop something in my course that is under review right now. I mean, I've shifted a lot of things in my own teaching that I can't write up and publish it all. But I developed a dry lab, because I teach the organic lab, that is basically about slowly building them up. If you are familiar with the jigsaw, it's basically a jigsaw. And we just curated a set of spectra that they would work on in a jigsaw fashion, interpreting, going up from simple to complex. Hopefully it will come out, soon. It's under review in Jacob. I think he had one, and then we can come up to it.
So I thought that was really cool because, it's a relatively simple concept. You have the spectra and you have the various different kinds of data. It was funny because the last time I looked at, I'm an organic chemist by training, but the last time I looked at an NMR in any serious detail was 5 or 6 years ago. But you kind of remember that. So I guess what I'm asking is that this is one very simple aspect of teaching organic chemistry. Do you get I'm just gonna for me the hardest part is still molecular orbitals. Could you apply how could you have you thought about what are the various other aspects of teaching organic chemistry that you're kind of thinking about applying it next?
Yeah, so we aren't looking at orbitals, but we are looking at other representations because what we're particularly interested in is the translation between representations. So going from a Lewis structure to a Newman projection or something like that, and what is the reasoning behind that and the visual spatial things that happen. And yeah, that's somebody's doctoral, somebody's dissertation that they're working on right now.
It's really, I mean, it'd be really funny if you all of a sudden found out the molecular the actual atomic plastic models don't actually do anything for people or something like that.
Yeah, it could, and eye tracking could be a helpful thing for that. But I know people are maybe looking at that in other ways. But I hadn't thought about the molecular orbitals, and I know I've heard people argue about, for example, whether VSEPR should be taught and are these things or hybrid orbitals, is that useful in organic chemistry? And so potentially you could answer that question. And I think the other interesting thing is looking at it in terms of a progression, because you don't really learn to understand those things in organic 1 or 2, right? You keep working with it, and you still evolve your understanding, I think. So what next?
curious, in your chart of how expert the various people were, I noticed that the graduate students were near the top, but one graduate student was down at the very bottom. Is that person still a graduate student?
I don't think that my IRB would let me find that out, but, you know, it wasn't just, we captured their experience in a number, but we tried to recruit people who were in organic labs, but, you know, if they were, for example, a first-year graduate student, they were really just an undergraduate not that long ago, right? So they might have been more closer to that group than the others, and I think that's probably what that was. But I'd have to look back at the data. Yeah.
So another question is, do you add an element of retention to any of these tests? Like where you have the same student who does the same or similar tasks like monthly and like even like a year after they've taken organic? Or I'm just curious how that factors into the...
You know, we haven't done that. I think one of the original ideas for doing this, the person who was, you know, who kind of put the idea in my head of looking at NMR interpretation this way is Brian Coppola, who's a colleague there, and he had talked about this, but, you know, he just never got around to doing it. And he had this idea of like, you know, of using, if you could get the eye tracking set up in such a way that you could use it to watch them over time. I don't know even if in a single year, you know, what you would see maybe at the, you know, when NMR is first introduced towards the end of the term, or, and then, you know, over time for undergraduates in an organic research lab, I think would be really interesting, rather than following the coursework, because I suspect that that's where a lot of the knowledge is being developed. But yeah, that would be really, but maybe starting in organic too and following them from there. Yeah.
So, yeah, so basically you get this data and you kind of figure out what they're not getting.
Yeah.
And you go back and adjust the assignment or the teaching or the activity in the classroom to try to improve that.
Yeah, so you could, yeah, that would be the idea, I guess, of doing the eye tracking, though. You couldn't do it with that many students at a time. So would it be, yeah. So it would be hard to do that.
So I can do that.
Yeah, exactly. In the way, you could potentially do that. I think in the way that, you know, the writing, for example, everyone can do the writing, and so I can use that as a good diagnostic thing. But for the eye tracking, I'm not quite, you know, I couldn't do anything in real time probably. But certainly you know, as I said, man, I've changed so much. For example, like, when do I introduce tables? I hardly ever, you know, I wait to introduce the tables because they hold on to the NMR table, and everything has to know like it's the law, and they don't want to let it go. So that's one big shift.
But that's helping them kind of build that implicitness, where they're starting to recognize implicit because they don't have that law to follow, and that's a good thing.
Yeah, and I think it's helped, but I haven't looked at that, and I guess I need a different instrument to see whether or not it's really doing what I think it's doing. But yeah,
fascinating. And I love the cultural teaching. And you brought students up there, they come back to Michigan, and then they go out and do their thing, and they're never going to forget that experience. And they'll bring it around. It comes around.
Yeah. The graduate students on this project are
incredible. Yeah.
The person who did most of the work, this is Jeff right there, and then so Katie Hasbein, she was at Portland State. Some of you might have known she did work with Jack Rivera, and then came and did a postdoc briefly, and then Danielle there, and you know, she was like, how can I keep working on this? Because they just want to, you know, it's such a cool experience. And
that's cool.
Yeah.
Went from the frozen tundra to hot, humid Purdue this summer, so that's pretty good contrast there.
So one more question I have about the NMR one really interests me. Do you have a control group of people who are not scientists, like they have no idea what they're looking at, and they're just, would that be useful? Do you think? I mean, is that?
Or the freshmen.
I don't know. I mean,
the English majors. I mean,
maybe not a complete control, but like maybe at the first introduction of it or something, because we really did start with them at the end of organic too.
Right.
So we didn't get maybe with the very, very beginning of what we could. I don't know what someone who did it would make of it.
I guess my question is like, is the human eye just naturally drawn to like points or circles or that kind of thing? Huh.
It could be. Yeah, I know people are developing apps. There's a company called Alchemy that we see around, and they're developing apps that help students like learn mechanisms with kind of train them intuitively based on the visuals rather than other things. I have no idea if they, what that means, but yeah.
Yeah.
I was just looking up here. In 2019, we had a speaker that was talking about citizen science in Alaska. And it was a very interesting concept because they actually would take these native peoples, not necessarily college people, some of them school people, and teach them the basics of chemistry by water sampling and soil sampling and whatever else. But it was a really interesting talk.
Yeah, so my colleague Carrie Pratt, who is up there, she has been involved in a bit of that because she does not only the snow sampling, but I think also for atmospheric things. So like
air samples.
Yeah, like for air quality things, because there are some outside of, I think it was North Pole, Alaska, we're talking about where the air quality is really bad because they use a lot of wood burning stoves. So she did it with that project too. Yeah, it is really fascinating because of what they're experiencing up there, there's a lot of things that you could do. But some of the techniques like the ion selective probe, I think the sensitivity is right that you could look in, you could get water samples from anywhere. You could use it in Michigan and look at, our water there too. So, yeah.
Looking at the pictures, I'm a little, it doesn't seem obvious to me that they would be using wood-burning stoves. I haven't seen
Yeah.
wood.
Well, not here, in another part of Alaska. So North Pole, which I think is closer to Fairbanks, which is really, really different. The temperature difference and the vegetation. They have trees there. Yeah, and they don't in Agave at all. Yeah, it's barren. Yeah, in that way.
All right, well, please join me in thanking our speaker. So thanks everyone. Our next meeting in December is going to be at the Lucky Lab in Northwest Portland. Just stay tuned for a flyer announcement with all the details and address, and we'll look forward to seeing you there if you can make it.